Prova. Prova. Prova audio.
Okay.
So, hello. I'm glad to introduce to you Leon Hoffman, that is collaborating with us since maybe quite long time. He's has been graduated at the Tel Aviv University some years ago, not many. Then he had at the Texas University the PhD, and after that he's working for the Catholic University of America, sharing his time principally on the Tel Aviv University and Goddard Space Flight Center. His field of interest is the solar corona, the plasma solar corona. He's working on MHD and kinetic model of plasma corona. We are collaborating since maybe about 20 years after the SO start of the SO mission, and he's some way helping us to interpret the data that we have of solar corona, mainly on the things that is the topic of this talk, that is the slow solar wind. We have a plan to move also to the fast solar wind, but before to do that, we will try to understand a little bit more detail of the slow wind. Essentially, we give this collaboration, we give the diagnostic of the data and the observation that we have in the ultraviolet visible light, and Leon use and help us to interpret the data with the model. For now, MHD model, multi-fluid model. This is the task for this talk.
Okay, thank you for the kind introduction. Okay, I'm going to tell you about the slow solar wind sources and some related background stuff. So let me see, where is the... Okay, so schematically what you see here is the solar wind coming from the sun. This is from NASA Visualization Studio, and in this case impacting Mars. There is no magnetosphere, so it impacts very directly. So here is the brief outline of the talk. I'll give you the introduction, impacts of the solar wind, observations of the slow solar wind sources, recent and planned, hypothesis on slow solar wind formation and observational constraints, and the numerical modeling of the slow solar wind sources, finally summary and conclusion. So some of this work, as you've heard, was done in collaboration with Silvio and Lucia, but also with a larger group where we had an EC workshop on the slow solar wind, and some of the results I'll show were derived in that workshop as well, under the guidance of Lucia and myself as a co-organizer of that. So here is a brief introduction for those of you who are not working on the solar wind. As you can see, this is the solar wind at the minimum corona. So this are measurements by Ulysses that flew over the poles of the sun. So the nice thing about the solar minimum, the structure is quite simple. There is a separation, relatively speaking, between the fast wind that reaches about 800 kilometers per second on average, and it's quite steady and low density. The colors here also mark the polarity of the magnetic field. And in the equatorial regions, we have very variable and slow and high density wind. And this is where we're going to concentrate. Now, the Earth, when it rotates around the sun, of course it's not to scale, encounters both types of wind because of the heliospheric structure, as evident from the heliospheric current sheet, for example. During solar minimum is warped. So there are sectors where the Earth passes through slow and fast wind. I hope I'm not obscuring the view from... Okay, so this is at solar maximum again. You can see highly variable wind that also appears at higher latitudes. So there is no longer a simple structure of a dipole-like streamer belt, but we have streamers at higher latitudes, and we have slow wind in all of these regions. So this is our schematic representation of the sort of the ballerina skirt, as it's been termed, this heliospheric structure, and you can see the planets here schematically again orbiting the sun. But this is not only schematic. Now I have to turn on the let me see. Yeah, yeah.
So I think it maybe doesn't work. Oh, no, here.
It should work if I can catch it. Oh, okay. Okay, so anyway, but it's quite obvious also without an animation what you see here. This is from a recent prediction. You see it started on March 18. Actually goes forward here over some few days, that uses a global heliospheric model. This model is called Enlil. And what you see here, this is their radial velocity, and this is the plasma density. So you see the various streams of the solar wind, and they have this Parker spiral, what's called a spiral structure, because of solar rotation. And this is basically as this is the Earth here. So as the spiral here rotates, and these are the stereo spacecraft, these dots here, the red and the blue. And this is the cut in the perpendicular direction. So you can see how the solar wind speed varies. This is the plasma density at Earth, and this is the stereo. This is quite a quiet period now because there were no solar activity, no sunspots. So it's very quiet and very steady. You can see the solar wind is measured at the stereo spacecraft, and at the Earth this is the radial velocity, and this is the plasma density. So, okay. Now it's supposed to be a movie here as well. I hope it's. Yeah, okay. Maybe I should, after all, use the. Yeah, it's not available. No. Okay, anyway, so what you see here is a very clear presentation what happens to the magnetosphere as the result of the solar wind interaction. So even without storms or any activity, you have a ram pressure from the solar wind, and because the Earth is surrounded by magnetic field, you have a bow shock that forms in front of the Earth, and then the magnetosphere gets extended, and here you see the auroral oval. This is where the charged particles reach the poles. So interestingly enough, beyond the space weather effects, there is also an important aspect of the magnetosphere with respect to the erosion of the atmosphere. So the Earth is losing atmosphere basically because of the solar wind interaction, among other things, at a rate of 3 kilograms per second. It sounds a lot, but it's not that much. So fortunately, we have the magnetosphere that protects most of the atmosphere from the interaction of the solar wind. And then the erosion is not that high as to deplete the Earth from the atmosphere in a few billion years. But this is not the case at Mars, for example. So at Mars, from the results of MAVEN spacecraft and some modeling, it became evident that the main reason Mars lost its atmosphere was the interaction from the solar wind. So the solar wind is not. There is also an aspect of habitability of planets. If we're looking at planets, if they don't have a magnetosphere, and there is a solar or stellar wind, they can lose their atmosphere fairly quickly. And this is basically the auroral oval again shown here. This is a measurement in the far ultraviolet actual measurement of the impact of the charged particles. So now the next exciting thing that's going to happen in solar physics is the launch of the Parker Solar Probe. And you can see here the list of objectives, so science objectives of the solar probe. You can see that one of the main objectives, the first objective, is to trace the flow of energy that heats the solar corona and accelerates the solar wind. So that means that understanding the current state of the solar wind is very relevant to the goals of this upcoming mission. Okay, then we also want to know the structure and dynamics of the plasma and magnetic field at the sources of the solar wind. Okay, so this is again something that we are already been doing for a couple of decades, as you said, and to understand the sources. So what you see here schematically, this is the view from LASCO at 30 solar radii. Okay, and these lines show the orbits of Parker Solar Probe. So basically, the solar probe will actually go through streamer structures. Okay, so it will be able directly sample the plasma, especially the proton and alpha components of the plasma in these structures. Of course, it will take time before it will reach the inner 10 solar radii, but the first orbits inside this 30 solar radii will be quite quickly. So this is artist's representation of the solar probe. You can see the thermal shield and the various instruments here. So there are particle instruments, field instruments, and also visualization. So you can see these are the list of instruments. So you have the solar wind electrons, alphas, and protons investigation. So this is directly relevant, you may say, to our modeling, because it will measure, although not oxygen as we've been doing, because we have the optical information from oxygen, but alphas definitely and protons will be measured. We have the wide field imager, okay, and the fields experiment, okay, that will measure all kind of waves that coming from the solar atmosphere. And then there is the integrated science investigation, which is unfortunately spelled out as ISIS, but it's anyway. So this investigation has two instruments that will monitor electrons, protons, and ions that are accelerated to high energy. So these are the high energy species. This is not the background solar wind. Anyway, but you can see that we will have those instruments that will measure. And then the heliospheric origins, which is the theoretical studies led by Marco Velli. So now you can send your name to the sun if you wish. Actually, you can put your name on a little disk that they're taking on the spacecraft. It's still available online. I already bought my ticket, so you can do that as well. So, moving forward, these are the typical parameters of the slow and fast wind. As you can see, the number density is quite high compared to the fast wind. The bulk velocity is about a factor of 2 lower. Proton temperature is lower, and the electron temperature is higher. So that is definitely shows us that we have different heating processes going on in the slow and fast wind. Then the alpha particle temperature, again in the slow wind, they are much cooler than in the fast wind. The magnetic field strength is about the same at 1 AU. It's about 6 nanotesla. So here what you see is the results from stereo spacecraft that show the basically some processed white light data that show the structures associated with the slow solar wind as they propagate. This work, by the way, you can not see for some reason the lower part of that projection, but it's the work by De Forest et al. So now what you see here, this is the larger field of view. You have this continuous stream of structures. This has been seen also by LASCO, but with stereo, you have images that look back from the sun, the heliospheric images. So you can look how these structures propagate away towards the Earth. And then it shows you that we have something like onset of turbulence. Of course, they cannot resolve turbulence directly, but they can resolve the large-scale structures that are associated with the cascade that eventually can lead to the small-scale turbulence. Here is another zoom of this result by De Forest et al. Okay, so now these are the white light observations, and you can see here that they have been observed since by Shili et al., where they looked at these little what they thought were blobs, but actually they are little arcs, because when you take another view from stereo, this is again from stereo, you can see that this thing that looks like a blob is basically a little arch. So then you have these blobs propagating outwards, and then when you trace them, you get the fast solar wind. So the basic process is that you have these flux structures that disconnect from the streamer structure, and this requires input of energy. If you heat the streamer, then eventually the internal pressure there will build up, and then it will drive those disconnected structures. So you have non-steady heating is another possibility that can lead to that. And this is a recent result from Vial and Morlidas that did a detailed analysis of these propagating structures, showing how they escape into the heliosphere. So this is one of the slow solar wind manifestations. Okay, these are the in situ observations that show another effect that is related to what we are doing, is basically the FIP effect. That means in the slow solar wind there is a different ratio of heavy elements and light elements compared to the photosphere. Okay, and also in the fast wind. Okay, but in the slow wind there is the FIP effect is higher. So some elements, again, is there a way to leave this? But anyway, so we don't see the lower axis here, but you can see that depending on the element, this is helium, I believe, and then these are the high FIP elements. So you can see that they are enhanced. Their abundance compared to the photospheric abundance is enhanced. And this is interesting, because when you look at these particles far from the sun, this is work from Forsteiger, you can see these velocities of the slow and fast wind. This is the fast wind velocity and the slow wind velocity, and you can follow here, for example, this is the silicon to oxygen ratio, so it's highly correlated with the speed of the solar wind. So this is from measurements from Ulysses. So you can see again in the slow wind there's the measurement of the FIP effect, and then this is various elements again in the fast wind. So the enhancement is different by a factor of 2 or more compared to the fast wind. So what it tells us basically that the ionic composition is important, and this is one of the results again by von Steiger et al. That shows the clear separation of the slow solar wind and the fast solar wind, but that can be found just by looking at the ratio of abundances of oxygen ions. For example, oxygen 7 plus over oxygen 6 plus times so compared to carbon 6 plus to carbon 5 plus, and when you put these on the scales, on the y-axis is the oxygen ratios, and here the carbon, this line where the product is 0.01 separates this fast wind. This is what is found in those slow wind and fast wind measurements. So again, it tells us that the minor ion composition is also a signature of the type of wind we have. So in the slow wind, we'll have different ionization, different ion ratios, different charge states than in the fast wind. So this is a very important result from von Steiger, which we also adopted in our EC work, in our report on the slow solar wind sources. So the other important aspects are the kinetic aspects, and that has, again, in the fast wind, we typically have turbulence, a turbulent cascade of energy from small scales to high scales, sorry, the other way around, and then we have the fluctuation spectra that goes as -5/3. It's called Kolmogorov spectrum. And if you look at the result, this is by Teloni et al. 2015. This has been measured in the ecliptic fast wind. Okay, so they see this separation. The thing is that it's very hard to measure these higher frequencies here. So these are, I believe, are results from cluster that goes into the solar wind once in a while. But you can see the separation of scales, and also you can see the dependence on the distances for the separation of scales. Now, because we know that this plasma exhibits some temperature anisotropy, this measurement result from many spacecraft. This is, for example, from wind data, and there are similar results from Helios data and ACE. There is a temperature anisotropy in the solar wind. That means that the temperature perpendicular to the field is different than the parallel temperature. And if you make many measurements of this property, you find that the distribution fits into this diamond shape. Okay, this is work by Hellinger et al. 2006. And if you put it as a function of beta, you find that you have this diamond structure. But then, to understand the structure, one can understand it by plotting the stability threshold for various instabilities. So here we have the mirror instability. This is the ion cyclotron instability, and we have the fire hose instability. So that these instabilities are driven by temperature anisotropy. So what it tells us that this shape is where the plasma can sustain stability for the particular value of beta and isotropy, because it's going to be below the threshold of these two instabilities. So this tells us what kind of measurements to expect in the solar wind. Now, to do what? Okay, yes. Yeah, don't worry about it. Yeah. So, okay. So now, what about waves? As we said, one of the possibilities is that we have a wave-driven wind, and there is evidence of waves even from ground-based data. This is from Tomczyk et al. That measure the basically Doppler fluctuations using a comp instrument. This is in Mauna Loa. So they find that there is a lot of wave fluctuations in the lower corona. Unfortunately, they only find an amplitude that is too low to justify the acceleration and heating. There could be the question of whether they have enough resolution and so on to determine the actual amplitude of the wave, or they do some integration over the line of sight that averages them out. But in principle, there is plenty of evidence of waves from also from other spacecraft, starting from SOHO and TRACE, then SDO. But this is sort of the ground wave. But the wave flux is in this measurement is too low, but there are other measurements that show that it could be sufficient. Now, if you look at the waves, the wave amplitude, what you see here is the distance from the sun, and on log scale. Okay, so the Earth is about here, 215 solar radii. So you can see the various measurements using various methods. For example, this is spectroscopic methods here, okay, and some of it is UVCS. Then you have what's called IPS measurements, so interplanetary scintillation measurements that show evidence of waves. So this is what we know. This is this empty region here, and that's where solar probe will provide data about the waves. So in this region that has not been explored yet. So then you see this is the theoretical curve that shows if we have waves, how can they propagate through the heliosphere. And then it is possible that some of that wave energy is responsible for the acceleration and heating of the solar wind. So now this was the result of our ECTM workshop of the various theories of the slow solar wind sources. So some of it I discussed here. So we have these results of interchange reconnection, for example here, where we have reconnection between open and closed flux that injects the energy into the solar wind. We have turbulence that can work on open field lines, and then again some other form of reconnection. This is again, this is a pseudo-streamer. Okay, pseudo-streamer is a streamer where the polarity is the same on both sides. Here you can see the polarity is opposite, so you can generate reconnection here, but here you cannot reconnect these lines because they have the same polarity. So you have to have some intermediate opposite polarity to provide the wind. There could be also acceleration along the channel. So this is sort of the summary of all the possible. So this is, now we are going to our collaboration results where we discussed the UV streamers, and what you see here, some results that show the streamer structure in magnesium-10 emission line, oxygen 6 and Lyman alpha, and you can see that the structure is quite different. There were many studies including our collaborations that tried to understand this effect. And of course we only see some ions with enough intensity, because their abundance is really very low, to get the information on the structure. But there are many other ions that show that should also result in different streamer structure. For example, another ion that is observed from Earth is the iron 15 or 17. They observed in the green line, so they also show different structure from the white light streamers. So there were a continuous effort trying to identify these results, and we have and they, together with the white light and the spectroscopic observations and in situ, they provide observational constraints that all the models that developed the structure must maintain. So we have the UV constraints, we have the spectroscopic observations in the inner corona, in situ observations far from the sun, and we have the temporal variability. So we need to constrain those results. So how do we proceed to do that? So the simplified modeling approach is to use MHD models. So the first, you can see here a set of MHD equations with the big simplification that instead of using a full energy equation that needs to specify the heating terms and so on, it uses a polytropic index. So that polytropic index, because it's different from 5/3 from the adiabatic index, basically indicate that you put energy into the plasma. Okay, so then using this polytropic model, this was the first sort of early results, used the 3D models with the polytropic model. This is the results from computation by Mikic et al., where they tried for many years to predict, you see this from 94, the last one here is 99, the structure of the corona before eclipse. So they used the polytropic model basically to do that. And you can see there is, globally there is an agreement, but if you look into detail, there's definitely the detail are different. Now, so it's not enough just to use a polytropic model. So the next step is to incorporate some thermodynamic terms that include heating and heat conduction and so on. And they have done that. Sorry, again, this is the citation is here. So this is the prediction, and this is the eclipse observation of 2017. Okay, this was in the US. So you can see that they are getting much better. You can see a lot of, this is a model. Okay, so you can see a lot of fine structure, brighter, darker regions. So the agreement is much better. But of course, still it's not the same. It's still, there's quite significant difference. But we're making progress. Okay, the other thing is the wave-driven wind. This is a model I've been working on where the wave-driven wind is incorporated explicitly, not by WKB terms that put in basically an average energy flux, but actually driving waves explicitly from the boundaries. So you can see here, this is in this case I inject alpha waves, so you can see these fluctuations in velocity associated with the propagating waves. So the waves in open field regions where we have the fast wind, they can freely propagate, but these alpha waves, they cannot propagate in the closed field streamers. Okay, they cannot propagate there, and because of the structure of the alpha speed and the direction of the field, because they propagate along the field. Okay, so now in order you can do, this is the animation of these waves that being injected. So you can see that they're sort of become trapped in streamers. So they can cause heating of streamers, but they don't reach the stalks of streamers. So then the waves can, these alpha waves, they can heat and accelerate the fast wind or the open field regions. Now, however, you can think about other wave modes. For example, you can inject fast magnetosonic waves or kink mode. And here, they have no problem of propagating perpendicular to the field. So you can see these waves are now inside our streamer structure. These are the density perturbation. This is the log of the density. This is the radial velocity, electron temperature. These are the current sheets associated with the waves and the velocity components. So you can see here, again, with the fast wind, yes, they can propagate inside the streamer. There are triple streamer structure here. So this is explicit wave model. So the problem is, in order to model this, you have to have very high spatial resolution over the structure that you inject the waves, and that is a limitation for global models. You cannot really today do it in global models, only in a localized model like that. However, in global models, they use this is a result from Van der Hulst et al. They use WKB alpha wave pressure terms. So they just put them in by solving an additional energy flux equation. And here you see this global model that shows the various components. This is the temperature. This is they have the parallel and perpendicular temperatures in this case, and the flux of energy you can see here, and they can model sort of the heliosphere much better than without the waves. So you can see here this is the previous model. Okay, this is stereo B171, stereo B195, and this is the current model. This is the previous model. So the current model making progress, so you can see more detail, better agreement with the structure. But of course, when you look closely, there is still the color table is similar, so it's good. So moving forward, the problem is, okay, let me just switch back here. Now these lines basically show ions. Again, the assumption is that they are completely coupled to the protons and electrons, which is a good assumption in lower corona. But when you go farther up, and farther up doesn't mean that much. It could be maybe halves already above the surface. They already decouple, okay? And in order to study the decoupled state of these ions, you need a three-fluid model. So this is the next approximation from MHD. But there are some dramatic differences. So first you solve, okay, you have the continuity equation is separate for the each ion species. In this model we just neglect the electron inertia and use it to obtain the Ohm's law. We get the electron velocity from the Ohm's law. But what you see is that you have three equations of continuity, or two, and then you have two momentum equations, okay? And then the energy equations, you have one for each species. And you have a separate electron, proton, and ion velocities. So what happens is basically that you have this term here. This is the gyro-resonant frequency, basically what is written here. If you remember from your E times B over MC is the gyro-resonant frequency. So basically you have very fast process of gyro-resonance happening here, and it depends on the difference between the electron and the ion speed. Okay, so now you have to account for this. The other terms you have are these terms, which I will discuss in more detail. This is the viscous term, and this is the Coulomb friction term. So basically there are collisions between, of course we know there are binary collisions, so in a multi-fluid approach you have to take into account the collisions between the fluids, between the electron fluid, the proton, and whatever heavy ion you use. So this is very important term as well. You have the separate gradients of pressure of electrons and the ions. This is your from your polarization electric field, okay? So because the electrons are lighter obviously than the ions, so technically their scale height should be much higher, okay, than the heavy ion scale height, but they cannot separate because of the electric field keeping them together. So this is explicitly written here. So all these differences, and if you look at the Coulomb friction terms, they need to be solved explicitly. So you can see these are basically collision terms that depend on the differences of the velocities between the ions, electrons, protons and ions, electrons and ions. And there are some correction terms, and these are the full collision terms. So everything is solved together self-consistently, including all the collision and the Coulomb friction terms in this model. These are the energy exchange terms. They are also solved self-consistently. So you can see that if you compare it to regular MHD, it becomes a little bit more of a headache to solve it. So these are the energy exchange terms. So again, you have the three fluids, so they all exchange energy. So if you start with different temperatures, when the collisions are small, okay, this collision term, then these temperatures remain different. But in the lower corona or in the high density region, these temperatures very quickly equilibrate, and we see it in the solution basically. So these are the solutions of the multi-fluid code. This is in 2.5D, showing the streamer structure. So this is our proton. So you can see the streamer lines. So this is the outflow of the protons, and we have the strap protons. So the streamlines here are very small. That means that they're not moving, right? Now, if you look at the helium structure, you can start seeing the effects of settling, okay? And this is for oxygen. So you can see that the settling is different and the structure is different. But what we observe so far, although there were some maybe unpublished observations of helium, but we observe oxygen and magnesium maybe. So magnesium we have imaging, right? So this is what we have. But with helium, which is an important component of the solar wind, since it carries significant fracture of the energy and mass flux, we also see this structure. This is the electron temperature. Okay. So now, moving forward, yeah. So now we can take start playing with our ions, heating them in various ways, and looking how it affects the results. So what you see here, this is the proton temperature, and here, this is the oxygen 5+ temperature. So we heated it the same way everywhere in a axisymmetric way, but because of the interactions that I showed in the different terms, basically in the closed field region, the oxygen 5+ is cooling because it exchanges energy with protons and electrons. So very quickly, you cannot even heat it to these temperatures here that you see in these bright regions, because inside the streamer, the interaction is, the energy exchange is very strong, so it becomes much cooler. Okay, and this is your electron temperature again. So, which means that although we can do some simple experiments like that and change the structure of the heating term, but it turns out that even if we do a radially spherically symmetric heating, the structure of the streamer will predetermine the results. And I'm trying to switch. Yes. So this is similar result for magnesium. Again, this is work not seen here, but that we did in collaboration with Lucia and Silvio. It was published in UpJ, I think 2013, maybe. Yeah, yeah. So you can see the magnesium structure. You can see the density contrast that is different between the center and the flanks of the streamer. This is the proton density, and this is the outflow speed of the ions and protons, and these are the temperatures. So again, very strong heating, but it's more, the heating is closer to the sun in this case, because it's constrained by observations of very high magnesium temperature. But inside the streamer, the energy is exchanged with the electrons mostly, and with protons, so we have cooling. I mean, although we dump heat, it immediately is divided into the other species as well. But because we have very low abundance of magnesium, that heat doesn't change the temperature of the other elements significantly. Okay, it only changes the, so only the magnesium itself is affected. So this is from our paper showing the results of the model. Okay, so you can see here, this is from the model, and this is from the observation. So you can see the dip in the emissivity of magnesium, oxygen, and the peak in the hydrogen structure, and we see very similar structure from our three fluid modeling results. This is more detailed comparison, again from our paper from 2011, and you can see you know, the slow solar wind, the fact that there's the closed field, you have trapped plasma, and you have some outflow at the edges, which is modeled reasonably well. Also, the density contrast here, as it matched quite well. This is for the dots, and the squares are from the measurements, and this is the model. So this is the temperature, where we have also very good matching. So we have this cooler region in the center and higher towards the outside. This is a two distances, 1.5, 4, and 2.2 solar radii. This is where the data were obtained. Now, in order to calculate the emissivity, we can solve and calculate these terms. So we have the collisional excitation, and we have the radiative excitation, which can be integrated by using the model output parameters, the electron temperature, the densities of ions and electrons, and so forth, and we can calculate this. And this is what we did in collaboration on this in this paper, and you can see a very nice agreement between the observational emissivity and the emissivity calculated from the model. You can see the structure, the two-legged structure of the oxygen, but there is an asymmetry, and I'm going to discuss it in the next few slides. What is the source of this asymmetry, the possible source. So then, for magnesium, there is not that much data, so we can see some plots from the temperature, because you had to integrate really over a larger region to get enough photons to get the line shape. So that's why there is only one point, while in oxygen we have, and just from that one point we build the whole model. So we have the temperature structure of magnesium, and the density structure, which is, you know, inside the streamers settled, and this is the proton structure, and the outflow speeds. So, and this is again a comparison with the emissivity. You can see that again it is normalized. The normalized quantities, not the absolute values, have very similar dependence both in the model and in the observation. And there's supposed to be an animation here. And let me see. Just a second. Anyway, so I'm moving on to a 3D model. Let me just see what is the... I'll try to switch it this way. Yeah, I am afraid that this is not going to work as well. But anyway, this shows the 3D structure of the coronal streamer. But all the information is also contained in the structure. So what you see here is a Carrington representation of the corona, where we have the angle theta, and this is the phi, this is the longitude. But here, of course, we have the information. We don't need to build as in Carrington map by waiting for 1 month. We have the information from the model simultaneously. So you can see the tilted streamer structure, and we have the, this is at 1.5 solar radii. You can see that we have this lower density structure, and there is some structure developed from as a result of the tilt, some accumulation of density at the boundaries of the coronal structure, coronal streamer belt structure. And this is the proton density, and this is the outflow speed, the proton outflow speed. So obviously in the center of the streamer the plasma is confined, and you have the outflow from the edges. And this is the ion temperature again. It is very high in open field regions, but inside the streamer, due to that energy exchange, they become cooler. So we can take a cut in the radial direction, as it's shown here for these quantities. So we see the density of the oxygen 5+ ions, the proton density, and this is the electron temperature, and these are the ion temperatures. So what you see here, and this is the current sheet, so you see quite good agreement with our 2.5D results, but of course the stock of the streamer is shifted depending where you're taking a cut because of the structure of our tilted dipole structure. Now this is a result that now is the subject of our new paper, where we try to understand the effect of the line of sight, which is quite clear that we have this bifurcated structure of the streamers, but sometimes we don't see that bifurcation in the oxygen. So it turns out, because of the integration of the line of sight of the emissivity, this is from our 1032 and 1216, so we can see that the black line, which represents the Lyman alpha, only changes the position of the stalk when the sun rotates. Okay, while the legs, the intensity in the legs varies depending on the field of view. So one leg could be amplified in one field of view, and then in another field of view will be the other one, and this is the result of the integration in our line of sight. So this could possibly explain the asymmetry, although we see that the streamer belt is quite symmetric, and also the dipole is expected to be symmetric during solar minimum, but still we see asymmetric emission from oxygen. So because there is no a priori reason why the oxygen abundance on one side of the streamer would be larger than on the other one. So what we find is, based on this modeling study, is the effect of the line of sight integration of our line emission. Now the next step is to take the structure, the real coronal magnetic field, not just the tilted dipole, and this is from the solar minimum. You see, although it's minimum, but still the corona is quite complex, and we're almost done. So you can see that we can use it in our model. This is a model of real magnetic field, so this is not, some of the streamers has not formed, but you see the formation of the streamers here, and this is the Carrington cuts, showing more realistic sort of field, but this is, again, it's at 1.5 solar radii. You can see the density of the ions and the protons, and this is the outflow speed. So there's more complex structure. This is the temperature structure as well. And this is, again, this is an example of the cut of a streamer, how it forms to a steady state, starting from the potential field surface model, which is just the approximation with fixed location of the cusp at 2.5 solar radii, and then depending on the thermodynamics, how much temperature and heating you put in, then the cusp can form at a different height. In this case, it forms farther out than in the original one. So just to show you, so you see the original one is 2.5, and then it extends to much higher height. So to summarize, so we have the solar wind, which is the background state of the heliosphere, which is important for the propagation of any perturbations that affect space weather, and also the steady state of the solar wind affects the conditions of the magnetosphere on Earth, or the atmosphere if the magnetosphere is absent. So now what we've found, based on observations and models, that there are different types of wind. Of course, we have the fast wind and the slow wind, and then in the slow wind we have not only different speed but also different composition, different charge states. This is evident from observations and also from the models. Then we want to connect the origin of the slow solar wind to various coronal regions, and this again can be done by looking at charge states and the ion abundances, as well from the spectroscopic observation as well as from the model. So we develop these numerical models that are constrained by observation on one hand as we build them, but they also provide us new unexpected results that can point to the processes that lead to the acceleration of the solar wind and the formation of the various structures of the sources. So then we have the upcoming Parker Solar Probe mission and also ESA Solar Orbiter, but Solar Probe will measure very close to the Sun where basically the slow solar wind is originating, and it will cross some of these structures. So that will definitely address the main questions that are still open regarding the acceleration and heating of the slow solar wind. Thank you.
Thank you to Leon. This started from overview of the processes to the detail of some work. Any question? I would like to ask.
Sure.
Maybe trivial things, but I always thinking about that. When you showed at the beginning the blobs observed by the stereo
Yes.
telescope, are you sure that this is low solar wind and not small CMEs? Because I have always in mind that the solar wind is something that we cannot see. We can measure but not see by it. It seems that this
Well, the thing is that you have the statistical sample of very large amount of these blobs of various sizes. When you place them on a space-time plot or velocity versus distance, you can see that they basically have the acceleration profile that is very similar to Parker's solar wind solution. So in that sense, this is what convinced. But you can ask what you're trying to ask, as I understand your question correctly, if it's only thermal pressure that drives the acceleration of these structures, or you have some magnetic forces like a slingshot. So yeah, so on average, yes, there is magnetic component, but they are sort of there is a very large spread, and on average you get the background solar wind profile.
Yeah, tracer.
Yeah, so they trace, they cause, because if they go a little bit slower than the solar wind, then they would be accelerated by the solar wind, and the other way around. Okay, so because they are small scale, they can be affected by the background solar wind structure. So on average, you get your solar wind profile, but it's, of course, it's a hypothesis. It's not proof.
Leon, regarding the interface slow and fast wind, have you been thinking of trying to reproduce in your model the observed anisotropy of the velocity, microscopic velocity distributions observed by BCS?
Well, basically, yeah.
The effect of the ion cyclotron resonance, basically.
Yeah, somewhat. In order to, well, it was done in another model by Van der Hulst et al., but it's a single fluid model on the other hand. So yeah, it is possible to include another energy equation for the temperature. So you have the parallel and perpendicular temperatures, and then there is a coupling term as well that couples them, but it's only going to be empirical because the model is not fully does not fully account for the instability. So the way it was approached in the single fluid model was that they artificially adjusted the anisotropy, so keep it below the threshold of ion cyclone instability. So it was not done self-consistently. So in that sense, it's possible also in the multi-fluid model to extend and include those terms and look on the effects of these of the anisotropy in the inner coronal.
In order not to be self-consistent, it should be a kinetic. It should be a kinetic.
Yes, yes, because the temperature anisotropy when you have the non-Maxwellian plasma, given the values of other parameters like beta, will result in the ion cyclone instability. So that will redistribute the energy in a way that is not, that only can be captured in a fluid approach approximately. So it has to be semi-empirical approach. But it's possible. The short answer is it's possible to include it. I have not done it so far, no. Mm-hmm.
There are, kinetic models.
Yes, I've done kinetic models for other purposes of the anisotropy evolution, but the issue is that these models are very small scale. Okay, so they only have a parcel of plasma that is maybe 1,000 kilometers cube. It is not a global model. It goes from the sun to 1 AU or even not to 10 solar radii. Yes, it's impossible because you need to resolve these small scales of the particle motions, right? Even even to do this with full electron and proton particles is very difficult, even in a small scale. So people usually use a hybrid approach where electrons are described as fluid while the ions are treated as particles, kinetically, yes, in particle and cell. So then if you have only anisotropy in ions and you have a separation of scales, you can say, okay, at least we treat the ions self-consistently. But then it's not possible so far to do a global model. There is a way, maybe a little bit, to improve it by looking at an expanding parcel of plasma. It's called an expanding box model. So you take your box of plasma, as it coasts into the heliosphere, it expands. So you can consider these effects as well. But it's not going to be the whole a global model in the kinetic regime.
That's all. Thank you again.
Okay.